Swayam Prabha, free DTH channel for education.
Good afternoon, everyone. So today we are going to talk about the difference in the second order ODE. Okay. Good afternoon, everyone. So today we are going to talk about the second order ODE. So already we have seen the first order ODE problem, and we have discussed about the linear ODE, and then y dash of x plus p of x y equal to r of x. Then we discussed about how to obtain the solution using separable ODE, and then we obtained exact ODE, and we have seen the existence of uniqueness also. Now today we are going to see the second order ODE. So the second order ODE is in general, as we did in the last one, there is a implicit and explicit form. So here also you can do the same thing. So the implicit form I can write as x of x comma y dash comma y double dash equal to 0. I can write it, okay, or I can write it as y double dash equal to f of x comma y dash. I can write it. Okay, so these are the two formats I can write it for the second order ODE in the implicit form and explicit form. So this is occurring in many of the mechanical engineering problems, like vibrations, you can say, and in electrical engineering you can say that RLC circuit is there. So there also this kind of problems are going to come. So now we talk about the initial value problem. So initial value problem means what we need to give is that together with this equation, either one of these equation, together with that we need to give a condition like at the initial position. So you have to give that y of x naught equal to some let's say k naught. Okay, let's say k naught, and y dash of x naught equal to k1. Let me give. Then I call this one as initial value problem. Okay, so because I prescribe the conditions both places at x naught, so that is the reason it is called initial value problem, and these conditions are called initial conditions. So these conditions are required mostly to eliminate the integration conditions, because you are having y double dash equal to f of x comma y dash. So once you are doing two times integration, suppose I have something like, let's say like y double dash equal to 0 is there. So in that case, what you are going to do, you are going to integrate these twice. So first time integration is going to give you something like a. Second time integration, I'm going to get something like a y equal to ax plus b is going to come. Okay, this is a very simple one. Y double dash equal to 0. So you can see that there are two constants are there. In order to eliminate these two constants, you can use this condition. So for example, I can put y of x naught equal to y of x naught equal to k naught I can put, okay, which implies a into x naught, okay, a into x naught plus b equal to k naught is going to come. Similarly, I can put y dash of x naught equal to k1, which is going to give you a dash. Y dash is nothing but a. Okay, a is going to give you the answer as k1. Okay, because y dash is going to be a is going to be k1. Therefore, you are going to get b is equal to k naught minus a x naught is going to come. Okay. A x naught, where k is already known, so you can put that as k1 into x naught. It is going to come. So therefore, your solution is going to become like y equal to k1x plus k naught minus k1 into x naught. Okay, this is going to be your solution. Or I can simply write this as k1 into x minus x naught plus k naught is going to come. Okay, so this is the solution for this. So that means this is the known values given, so you can eliminate them. So that's the idea here. So for example, you have this condition y double dash plus y dash minus 6y equal to 0, y of 0 equal to 1, and y dash of 0 equal to 0. This is a initial value problem. Similarly, y double dash minus y equal to 0 is given. So in that case, once again, you can do the same kind of thing. So you are going to get it like again, this is called initial value problem. Now, same way, what you can define is that you can define something called boundary value problem. So instead of that, suppose this is given. Okay, suppose you have given some problem where you know the you know the initial position of that, and you know the velocity of that also. Okay, you know what is the initial position and what is the velocity of that also. You know. So in that case, you can find the answers for that. Similarly, you can do one more thing, which is called boundary value problem. So in boundary value problem, what you have is that you have, let's say, like two things are there. Okay, one is nothing but, let's say, y of a equal to k1 k naught, and y of b equal to k1 is there. Okay, means what you have is that we have two conditions are there. It is defined on an interval. For example, this problem is defined on an interval, let's say a comma b. Okay, for example, you can take our heat equation itself. So you have a heat equation here, which is going to have some kind of, let's say, like in the heat equation, time is vanishing. Okay, this is independent of time. So you have two positions are there. One is here, one is here. So this is like this is here. I'm getting like 300 degrees Celsius, and here I'm going to take it like 500 degrees Celsius. So these two ends I'm going to heat. Then I'm going to observe what is the temperature is going to be in the. So this is one such example. You can see that. Okay, y of a equal to k naught and y of b equal to k naught. So this one I'm just going to give some physical interpretation of these two problems. So what is it going to do? For example, if you consider your trajectory is okay, you are launching a missile or you are throwing a ball. Okay, for that case, it is going to follow some trajectory. Okay, so in the case of this problem, what you know is that you know the trajectory of the path is going to governed by this differential equation, second order differential equation. And y of x naught equal to k naught and y dash of x naught equal to k1. What it is going to say is that suppose this is my x naught. Okay, this is my x naught. Then I have at this position I know what is the y value I know. Okay, I'm going to give at x naught what is the y is going to be there, and then I am going to give y dash of x naught. So y dash of x naught is going to denote be the velocity. So at what velocity I'm going to throw, that I'm going to give it over here. Then from this one, what you can observe is that after certain stage, okay, y dash of, so here once I'm saying this one x naught, this is going to be like you can say t naught. Okay, so you are going to observe where it is going to land once it is reaching after certain stage. So x naught is given, let's say after some stage, okay, let's say like x5. So after 5 minutes, so x naught means 0th second I'm giving, 5 minutes, after 5 minutes I'm just going to get it, or let me say 5 into 60, so I can put like 300 seconds also I can put, okay. So after 300 seconds, what is going to be the position after? I have given the velocity, so the initial position is k naught, okay, initial position is given as k naught, and it is given that the velocity is k1, okay, velocity is k1. So I'm throwing a ball from here and I'm giving an initial velocity of like let's say 5 meters per second I'm giving. So in that case I have to see what is the velocity, where it is going to land after 5 minutes, whether it is going to be here or whether it is going to be here, that I can observe from this problem. That is called the IDP problem. Now if you come for the boundary value problem, what is it going to come? So here I have two positions are given to me. Okay, y is given, b is given to me. Okay, this is the position. I'm throwing with some velocity and it is going to follow some path and it is going to reach the it is going to land it in some places. Okay, some country it is going to land. Let's say I'm throwing some missile, it is going to land. So I know what is the initial position. I know what is the final position also. So in this case, you can obtain by solving this one, you can obtain what is the velocity of this one or what is the trajectory it is going to follow. Everything you can obtain from this boundary value problem. So this is the two important things. So here in the initial value problem, x naught is given, okay, and velocity is given. So you are going to find where it is going to be there after certain stage. So for example, if I say this is x5 or x300, then I got to find where it is going to be there. Similarly, if I have found here, I give a and b, then you can find the trajectory. But here you are going, you can calculate what is the velocity is going to be. So these are two different aspects of two different things about the initial value problem and boundary value problem. Okay, so you can keep it in mind. So other boundary conditions are there. So the one which I defined over here is called the Differential boundary condition, because I'm Differential boundary condition, or is otherwise called as fixed boundary condition, because I'm here, for example, in the case of heat equation, I am just giving constant heat over here, let's say 300 and 500. So in that case, this is going to be like this is going to give a fixed value over there. Therefore, this is also called as fixed boundary condition, or it is called as Differential boundary condition. So this is of this kind. Neumann boundary condition means what you can prescribe is that you can prescribe what is the velocity, okay, what is the value of y dash, okay, what is the value of y dash you can specify, y dash of a you can specify, and y dash of b you can specify. Okay, these two values if you can specify, okay, let's say this is k0 and this is k1, and these conditions are called Neumann boundary condition. Then we have one more condition called Robin boundary condition. In Robin boundary condition, what you are going to take is you are going to take a combination of these ones. So you are going to get alpha 1 into y of a plus beta 1 into y dash of a equal to c, okay, and alpha 2 into y of b plus beta 2 into y dash of b equal to some d. Okay, so this is called Robin boundary condition. Similarly, you can define periodic boundary condition also. The periodic boundary condition is something like y of a is equal to y of b you can define, and y dash of a equal to y dash of b you can define. Similarly, there are many other boundary conditions are there. For that, you can refer some of my lectures on partial differential equations, where you have something like inlet is there, outlet is there, and symmetric boundaries there, anti-symmetric boundaries are there. There are many other boundary conditions are there, but here we are just going to we are going to see only these problems, and mostly we are going to have only the initial value problem on twisted boundary value problems we will mostly solve in this engineering differential equations for engineering course. Okay, differential equations for engineering course. So we will see like these are all the examples for that. For example, y w dash plus 4y equal to 0 and y of 0 equal to -2, y of pi by 4 equal to 10. This is a boundary value problem. Okay. Similarly, y w dash plus 2y dash plus y equal to 0, y of 0 equal to 1, and y of 1 equal to 3. This is again a boundary value problem. As I mentioned earlier, you can take a heat transfer equation. Okay, the heat transfer equation of rod length 1 meter, 1 centimeter. Okay, so that also you can do a similar kind of thing. Let's say like, at one end you are getting 25, another end you are getting 75 degrees Celsius, and some parameters are given. Then you can say that this is called a heat equation. Okay. Okay. Now what I have the so that this is the one which I have already explained. What is the IVP and BVP we have given? So for a given boundary condition, the solution of the BVP may or may not exist. Okay, for this problem, for given boundary condition, even though boundary conditions are given, sometimes the solution may exist, sometimes the solution may not exist. So that we need to study. Okay, even if it exists also, it cannot be unique, or it does not exist also sometimes. Okay, it can be unique or it cannot be unique also. So the existence and uniqueness of boundary value problems are formulated using the form of existence and uniqueness theorems. Okay, that we are going to see. And then IVP and BVP occur for many engineering problems also. So that also we are going to see one or two examples. Okay. Now second order ODE. So this is a simple application. So second order ODE simple harmonic. So this is a simple application we can see. So you can say like suppose some dashboard or some spring is there where you are attaching some mass to that, then that is going to stretch it out and you are going to see what is going to be there. So those things you can stretch. So for example, you can assume an object of weight 9.8 kg stretches the spring to 20 centimeter. Then you can find the equation of motion if the string is released from an equilibrium position. Okay, with an upward velocity of 14 meter per second. Okay, so then you can find what is the period of motion you can find. So this one you can model it using second order ODE, which is called simple harmonic. Okay, so how do we do that? So for the modeling part, you can use the Hooke's law, Newton's second law. So according to the Newton's second law, what you have is that you have m/w dash, which is nothing but the force equal to mass into acceleration. So in that case, what you have, force is equal to acceleration. So if I say initial position I mentioned as y, okay, y of x naught is going to be that. Then I can say velocity is going to be y dash, and acceleration is going to be rate of change of velocity. Therefore, you are going to have f equal to ma is going to become like I can write it as m into y w dash. I can write it. Okay, this is going to be your Newton's second law. Okay, and then Hooke's law is going to say your force is nothing but your force is going to be inverse proportional to y. Okay, force is proportional to that y. So in that case, you can say that minus ky is going to come. So you can just both force should be the same. Okay, this is related to the Hooke's law. So in this case, what you are going to have is that you are going to match these two things together. Therefore, you are going to get my w dash. So this is given that according to this law, this is going to be, since you have forces acting on the opposite direction, you are going to get f equal to minus f1 is going to come. Okay, so therefore you are going to get f equal to minus f1. Therefore, my w dash plus ky equal to 0 is going to come. Okay, so these are all some simple physics problem or mechanical engineering problem which you may know. So that's the one we are developing. So this is going to be the simple harmonic equation. Okay, with many assumptions, like I don't consider about many other parameters. Okay, we will consider one by one. So simple one. So m y w plus ky equal to 0 is there. Then you can model this problem. For example, for the previous problem, it is given that w mass is like it is stretching 9.8. Okay, 9.8 weight is going to be 9.8. Okay, that stretches 20 meter per second. So that I am going to 20 centimeter per second, I think. Yeah, 20 centimeter. Okay, 20 centimeter it is stretching. Therefore, it is going to give you. So the stretch is going to be 20 centimeter. Therefore, what you are going to get is that the S is going to be 20 by 100 and converting it into unit the SI units. Okay, therefore I am going to have 1 by 5 here. And we know that mg equal to ks. Okay, so mass into gravity, acceleration is going to be k times the spring constant times the displacement. The stretch is going to happen. So therefore, you can obtain that if you multiply that. Okay, ks. So ks is nothing but 1 by 5. So you are going to get it like k is equal to mg is already known 9.8. So k it is given that mg equal to ks. Okay. So already S is known, mg is known, mg is nothing but W. Okay, W is already known, which is 9.8, and Ks is K into 1 by 5. Therefore, K is going to become like 9.8 into 5, that is going to become like 49. Okay, that 49 is going to come. So therefore, your problem is going to become like, you can put that values over here. So this is going to become like, this one is going to become like my double dash plus 49y is going to come. Now we can obtain what is our m also from here. It is given that W equal to 9.8. Okay, gravity we assume that 9.8. Therefore, W is equal to mg equal to 9.8. Okay, which is equal to m into 9.8. Okay, m into 9.8 is going to come. So 9.8, 9.8 cancel. Therefore, you are going to get m equal to 1. Therefore, this is going to become like y double dash plus 49y is going to come. And it is at the equilibrium position. Okay, initially it is at the equilibrium position, means that position I am just going to assume that it is going to be 0. Okay, y of 0 is going to be 0. Then what I have y dash of 0, that is going to become like minus 40 because it is going in the opposite direction. So it is stretching in the against the gravity. Therefore, I am going to get y dash of 0 equal to minus 40. So how do we find the solution of this problem? That we have to see. Okay, that we will see soon. The same kind of problem you can see that in the motorbike suspension, that we have the suspension is there, and you have the dashboard, etc. So that is going to come in a similar way. Okay, you can see that. So for example, this is one problem which we were working with European Space Agency and NASA for some Mars lander, where what we obtained was a similar kind of problem we obtained. So what is the problem is that we have lander is there. That lander is going to land in. They want to reuse the lander which is available for moon. So the moon lander they have to keep it in the Mars. Okay, they are going to send that to the Mars thing. So they need to understand whatever spring constant, because the gravitational force in Mars will be different, moon will be different. So in that case, they need to understand whether the spring constant at the dashboard which they designed for the moon lander is sufficient to use it for the Mars lander also. Means we can design a lander which can be landed in any of the planets which we can approach using the rockets. Okay, so for example, Mars lander can be landed in moon surface, or moon surface lander can be landed in the Mars surface. So those things they have to identify. So in that case, once again, the similar kind of things you need to do, because here also you have the spring constant and dashboards, everything is there. Then you have to do them. Okay, so this is the lander suspension which they want to study. So again, so here we are going to have some more thing once we are coming to the real world problem. So here we didn't consider in this problem, we didn't consider the friction, we didn't consider, and other process we didn't consider. Okay, but if we consider the friction of the system, then we are going to consider more properties are going to come. Okay, we are not considering many of the properties here. So one by one we are slowly adding. So if you are having friction, okay, then in the real world there will be some friction will be there. So in that case, what you are going to have, this is going to give you some oscillation. Okay, that is called damping. So it is going to like oscillations die slowly. That is we call this a damping. And we have air resistance, physical damper or dashboard is there. So that is going to support that. Now damping, what is damping? Damping is a friction force. Okay, damping is a friction force which is proportional to the velocity of the mass and acts in the opposite direction. Therefore, what you are going to get, you are going to get one more term over here. Okay, that is going to be again the same thing. Okay, plus your minus you are going to get the opposite direction. Therefore, you are going to get C y dash is going to come. Okay, C y dash, because it is proportional to the velocity of the mass and acts in the opposite direction. Therefore, this is going to become like minus C y dash. So I can put this over here. So this is going to become like then Cy dash plus Ky equal to 0 is going. Okay, where C is nothing but the friction coefficient. Okay, the friction coefficient you are going to get. So again, you can transform this into the, this is once again the second order ODE which you can So for example, this is another problem. So you are riding on a bike, okay, Hero Honda bike. The Hero Honda bike is like say 109 kilogram, and you assume that the rider weight is 67.4 kilogram. When the rider mounts the bike, the suspension compresses to 9.8 centimeter. Okay, this may not be reality, but I'm just giving some example. So 9.8 centimeter is compressed. Then comes to the rest at equilibrium. Okay, the suspension system provides a damping equal to 360 times the instantaneous velocity of the bike. Then you need to model this bike. So the bike and rider together need to model. So in this case, what is the weight we are going to consider? The weight is going to be like 176.4 because I am adding the weight of bike together with the weight of the person. Okay, it may not be reality because you need to consider some other parameters. So for this problem, we are trying a simple one. So I'm just assuming that the mass which is going to act on that spring is going to be 176.4 kilogram. Okay, so therefore, and it is given that it is stretching 9.8 centimeter. Therefore, I'm going to use that S equal to instead of 9.8 here. So here 9.8. So S is going to become like 9.8 centimeter. That will become like 0.098 is going to come. Okay, so once again you do the same kind of jobs. Then what you are going to get is that you are going to get your K is going to become like 1800. Okay, your K is going to become like, so in this case your K is going to become like 1800. So our K will become like, so in this case, so W is given. Okay, W is 176.4. W is 176.4, and your K is 0.098, and you have that C is going to be like, so you can, sorry, K is not 0.098, S is 0.098. Okay, S is 0.098, and you do again the simplifications of this. Then you are going to get K equal to 1800. Okay, and then you are going to get again calculate the W from the 9.8 etc. So you are going to get M is going to become like, in this case from this one you are going to get M equal to 18 is going to come. Okay, so then you can substitute over here. So M is known, K is known, and C is nothing but 360 times velocity that's given. So therefore this is going to become like, C is going to become like 360. So you can use that, and then you can formulate that. So this is going to become like 18 y double dash plus 360 y dash plus 1800 y equal to 0 is going to come. So this is going to be my model for this bike problem. Okay, so when a bike was in the air before contacting the ground, the wheel was hanging freely and the spring was uncompressed. Therefore, the wheel is 0.908 meter below the equilibrium position. Okay, so therefore we are going to get, y of 0. So in this case, you are going to get y of 0 equal to 0.098. Okay, you can just model it as a mechanical engineers. You can just do that, and then you are going to get what is your so that is nothing but your y1. Okay, so that is going to give you the y of 0. Similarly, you can find y dash of 0. You can put some conditions, and then you can find the problem, or you can put some other y dash of 0. You can find y dash of 0 also. You can find it. Y dash of 0 you can put it. You can put what is the value, and then you can find it. Okay, so these are the things you can develop, and then you can. So the solution of the problem is once again going to be obtained. Okay, we will see like how to obtain that. So in general, okay, let's come to the general theory. So in general, so whatever we have discussed so far, there are a few kind of problems we have discussed, but we are not going to discuss about the nonlinear PT most of the time. We are going to discuss about only the nonlinear ODE. We are not going to discuss about the nonlinear ODE most of the time. We are going to discuss about the second order linear ODE, and with variable questions, without variable questions only we are going to discuss in these lectures. So we are so in general, the second order ODE is called linear if it can be written in this form: y double dash plus p of x into y dash plus q of x into y equal to r of x. Okay, if r of x is simultaneously 0, then we say this ODE is homogeneous ODE. If r of x is not equal to 0, okay, then we say that this is a non-homogeneous ODE. Okay, so if it is not written in this form, then this ODE is called a second order nonlinear ODE. Okay, so here we are making the coefficient of y double dash as unity. If it is not unity, then what you need to do is that you have to divide that. Suppose it is not 0, you cannot divide that, but 0 means it is not going to come here because this is the second order linear ODE. Therefore, this coefficient should be at least non-zero. Okay, this coefficient should be non-zero. Then only you will have second order linear ODE is going to come. So therefore, this is going to be not equal to 0. Therefore, you can divide that and then you can apply the solution. Now, the next question is how do we know whether the solution is going to exist or not? So for that, we need to discuss some of the theorems. Again, this is going to be expressed. Okay, this is the same way. It is called linear. So you can express this way. So this is going to be linear with respect to 3 variables now. One is y, another is y dash, another is y double dash. In the previous one, we mentioned that in the first order linear ODE, it should be linear with respect to the first variable y and second variable y dash. Here it should be linear with respect to y dash and y double dash. In all these things, it should be linear. Again, we are not mentioning that it should be linear with respect to x. We are not saying only with respect to y dash and y double dash. If it is that, then we say that it's a linear ODE. Okay. So if it is a homogeneous ODE, I can just write this as L of in general, this is L of y comma y dash. So in general, we write it like L of y also. It means this is the same thing. Okay, so it's the same thing I'm going to write. So if it is equal to 0, this is homogeneous ODE. If L of y can be written as equal to R of x, and that is called non-homogeneous ODE. Y double dash plus into y plus y dash square equal to 0. Okay. So this problem we are going to see whether it is going to be a linear ODE or not. So let's consider y. Okay. Let us solve this problem. Let us solve whether this problem is going to be linear ODE or not. Now what I am going to check is I am going to check only this point. Okay, only this y dash square is it going to be linear or not. If it is not linear ODE, then you can verify that it is not going to be. So in that case, what you need to check is that I am going to check only this one. Remaining part you just verify it is going to be or not. So this one I am going to check whether alpha y1 plus alpha. So I am going to take this one. Okay, alpha into y1 dash, alpha into y1 dash plus beta into y2 dash whole square is it equal to alpha into y1 square, y1 dash square, okay, plus beta into y2 dash square. Is it true or not? That I got to check. Okay, so this is definitely not that because you are going to have here alpha square into y1 square is going to come plus beta into y2 square is going to come, but this is not true. Okay, therefore it is not linear ODE. Okay, so that's all. Now we are going to see the solution of the second order linear ODE. So similar to the solution of the second order first order ODE, what you are going to have is that the solution is defined in the same way. Suppose Kach is a function, okay, Kach of x is a function which is 2 times differentiable, okay, and it is satisfying this. We are substituting over here wherever y is there. We are substituting over here. So Kach double dash plus p of x into Kach dash plus q of x into Kach equal to 0 is going to come. Then we can say that this is the Kach is called as the solution of the second order ODE. Okay, on some particular interval a comma. If Kach is defined, Kach is defined twice differentiable. Okay, and replacing Kach by this respective value, we are going to get. That is the if it is producing the identity, then we say that this Kach is the solution of the second order linear. So instead of writing this y double dash plus p of x, y dash plus p of x equal to r of x, people also write this as, okay, this one they write it as d square plus p of x into d plus q of x, okay, q of x into y equal to r of x. This also people used to write. Okay. So this is called the differential. So this d is called differential operator. They used to write.